Page number 22. Now write and balance the equation for the above reaction. Since metallic oxide react with acid to give salt and water, similar to the reaction of a base with an acid. Metallic oxides are said to be basic oxides. 2.1.6 Reaction of a non-metallic oxide with base. You saw the reaction between carbon dioxide and calcium hydroxide, lime water, in activity 2.5. Calcium hydroxide, which is a base, react with carbon dioxide to produce a salt and water. Since this is similar to the reaction between a base and an acid, we can conclude that non-metallic oxides are acidic in nature. Questions. Why should curd and sour substances not be kept in brass and copper vessels? 2. Which gas is usually liberated when an acid reacts with a metal? Illustrate with an example. How will you test for the presence of this gas? 3. Metal compound A react with dilute hydrochloric acid to produce effervescence. The gas evolved extinguishes a burning candle. Write a balanced chemical equation for the reaction if one of the compound formed is calcium chloride. 2.2 What do all acids and all bases have in common? In section 2.1, we have seen that all acids have similar chemical properties. What led to this similarity in properties? We saw in activity 2.3 that all acids generate hydrogen gas on reacting with metal. So hydrogen seems to be common to all acids. Let us perform an activity to investigate whether all compounds containing hydrogen are acidic. Activity 2.8. Take solution of glucose, alcohol, hydrochloric acid, sulfuric acid, etc. Fix 2 nails on a cork and place the cork in a 100 ml beaker. Connect the nails to the 2 terminals of a 6-volt battery through a bulb and a switch, as shown in figure 2.3. Now pour some dilute HCl in the beaker and switch on the current. Repeat with dilute sulfuric acid. What do you observe? Repeat the experiment separately with glucose and alcohol solution. What do you observe now? Does the bulb glow in all cases? In activity 2.3 in figure 2.3, acid solution in water conducts electricity. Page number 23. The bulb will start glowing in the case of acids as shown in figure 2.3, but you will observe that glucose and alcohol solution do not conduct electricity. Glowing of the bulb indicates that there is a flow of electric current through the solution. The electric current is carried through the acidic solution by ions. Acids contain H plus ion as cation and anion, such as Cl- in HCl, NO3- in HNO3, SO4 2- in H2SO4, CHCOO- in CH3COOH. Since the cation present in acids is H+. This suggests that acids produce hydrogen ion, H+ in solution, which are responsible for their acidic properties. Repeat the same activity using alkalis such as sodium hydroxide, calcium hydroxide, etc. What can you conclude from the result of this activity? 2.2.1 What happens to an acid or a base in a water solution? Do acids produce ions only in aqueous solution? Let us test this. Activity 2.9. Take about 1 gram solid NaCl in a clean and dry test tube and set up the apparatus as shown in figure 2.4. Add some concentrated sulfuric acid to the test tube. What do you observe? Is there a gas coming out of the delivery tube? Test the gas evolved successively with dry and wet blue litmus paper. In which case does the litmus paper change color? On the basis of the above activity, What do you infer about the acidic nature of 1. Dry HCl gas, 2. HCl solutions? Note to teachers: if the climate is very humid, you will have to pass the gas produced through a guard tube, drying tube, containing calcium chloride to dry the gas. In figure 2.4, preparation of HCl gas shown. This experiment suggests that hydrogen ion in HCl are produced in the presence of water. The separation of H plus ion from HCl molecule cannot occur in the absence of water. HCl plus H2O is equal to H3O plus Cl minus. Hydrogen ion cannot exist alone, but they exist after combining with water molecule. Thus, hydrogen ion must always be shown as H plus or hydronium ion, H3O plus. H plus H2O, H3O plus. We have seen that acids give H3O plus or H plus ion in water. Let us see what happens when a base is dissolved in water. NaOH on arrow H2O, Na plus OH minus. Page number 24. KOH on arrow H2O is equal to K plus OH minus. MgOH2 on arrow H2O is equal to Mg2 plus twice OH minus. Bases generate hydroxide OH minus ion in water. Bases which are soluble in water are called alkalis. All bases do not dissolve in water. An alkali is a base that dissolves in water. They are soapy to touch, bitter and corrosive. Never taste or touch them as they may cause harm. Which of these bases in the table 2.1 are alkalis? Now, as we have identified that all acids generate H plus and all bases generate OH minus, we can view the neutralization reaction as follows. Acid plus base is equal to salt plus water. X plus M, OH is equal to Mx plus HOH. H plus OH minus is equal to H2O. Let us see what is involved when water is mixed with an acid or a base. Activity 2.10. Take 10 ml water in a beaker, add a few drops of concentrated H2SO4 to it and swirl the beaker slowly. Touch the base of the beaker. Is there a change in temperature? Is this an exothermic or endothermic process? Repeat the above activity with sodium hydroxide pellets and record your observations. The process of dissolving an acid or a base in water is a highly exothermic one. Care must be taken while mixing concentrated nitric acid or sulfuric acid with water. The acid must always be added slowly to water with constant stirring. If water is added to a concentrated acid, the heat generated may cause the mixture to splash out and cause burns. The glass container may also break due to excessive local heating. Look out for the warning sign shown in figure 2.5 on the can of concentrated sulfuric acid and on the bottle of sodium hydroxide pellets. Mixing an acid or base with water results in decrease in the concentration of ions H3O plus, OH minus per unit volume. Such a process is called dilution and the acid or the base is said to be diluted. Page number 25. Questions. Question 1. Why do HCl, HNO3, etc. show acidic character in aqueous solution, while solution of compounds like alcohol and glucose do not show acidic character? Question 2. Why does an aqueous solution of an acid conduct electricity? Question 3. Why does dry HCl gas not change the color of the dry litmus paper? Question 4. While diluting an acid, why is it recommended that the acid should be added to water and not water to the acid? Question 5. How is concentration of hydronium ion H3O plus affected when a solution of an acid is diluted? Question 6. How is the concentration of hydroxide ion affected when excess base is dissolved in a solution of sodium hydroxide? 2.3. How strong are acid or base solutions? We know how acid-base indicator can be used to distinguish between an acid and a base. We have also learnt in the previous section about dilution and decrease in concentration of H plus or OH minus ion in solution. Can we quantitatively find the amount of these ions present in a solution? Can we judge how strong a given acid or base is? We can do this by making use of a universal indicator, which is a mixture of several indicators. The universal indicator shows different colors at different concentration of hydrogen ion in a solution. A scale for measuring hydrogen ion concentration in a solution called pH scale has been developed. The P in pH stands for potence in German, meaning power. On the pH scale, we can measure pH generally from O, very acidic, to 14, very alkaline. pH should be thought of simply as a number which indicates the acidic or basic nature of a solution. Higher the hydronium ion concentration, lower is the pH value. The pH of a neutral solution is 7. Values less than 7 on the pH scale represent an acidic solution. As the pH value increases from 7 to 14, it represents an increase in OH ion concentration in the solution. That is, increase the strength of alkali. Generally, paper impregnated with the universal indicator is used for measuring pH. Figure 2.6. Variation of pH with the change in concentration of H plus and OH minus ions. Page number 26. Activity 2.11. Test the pH values of solution given in the table 2.2. Record your observations. What is the nature of each substance on the basis of your observations? In table 2.2, 4 columns are given. First is solution, second is color of pH paper, third is approximate pH value, fourth is nature of substance. 10 serial numbers are given. The solutions are saliva, before meal, saliva, after meal, third lemon juice, fourth colorless aerated drink, fifth carrot juice, sixth coffee, 7 tomato juice, 8 tap water, 9 IMNOH, 10 IMHCl. Now in figure 2.7, pH of some common substances shown on a pH paper. Colors are only a rough guide. The strength of acid and bases depend on the number of H plus ions and OH minus ions produced respectively. If we take hydrochloric acid and acetic acid of the same concentration, say 1 molar, then these produce different amounts of hydrogen ion. Acids that give rise to more H plus ion are said to be strong acid, and acids that give less H plus ion are said to be weak acid. Can you now say what weak and strong bases are? 2.3.1. Importance of pH in everyday life. Are plants and animals pH sensitive? Our body works within the pH range of 7.0 to 7.8. Living organism can survive only in a narrow range of pH change. When pH of rainwater is less than 5.6, it is called acid rain. When acid rain flows into the river, it lowers the pH of the river water. The survival of aquatic life in such rivers become difficult. Thank you, students. Please listen twice for better understanding. Hope you like the video and subscribe for upcoming videos.